Hello, this is Emad Mirabi. I'm going to solve a physics problem from tolc I exam. So let's read this problem and solve it. A cylindrical container placed on a horizontal table is filled with water up to a height of 1 meter. At which height should we make a hole so that the water jet pouring out of the container hits the table at the largest possible distance from the wall of the cylinder? So let me solve it like this. This is a cylinder and this is a table. Let's take this the level it is filled. So the height of the water in the cylinder is 1 meter. If we make a hole in this cylindrical container, water comes out like a jet and goes a parabolic path to hit the table like here. So we want this d, or distance, horizontal distance, to be maximum. If we go deeper inside the liquid, the velocity of the water jet will be greater, but it has got less time. It's got less time to travel in the air. For example, if there is a hole here, maybe the jet of water has more velocity, but it has got less time. It's got less time to fall down. The traveling time is less, so there is a trade-off. So at which height should we make a hole in this cylindrical container so that the d will be maximum? So I'll take this to be h, and therefore I'll take this to be h, and then the remaining is 1 minus h. First, I apply Bernoulli principle. If I apply Bernoulli principle between 1 and 2, so 1 is the level of the water, the top level of water, and 2 is where the water is pouring out of the container. So there are three terms: half of rho v squared plus rho gh plus the pressure term. So half of rho v squared is the pressure term, is a term related to kinetic energy in what dimension is pressure. This is the potential, this is the gravitational potential energy, and this is pressure, all written in pressure dimension. Okay, P1 and P2 are both the same because both of them are atmospheric pressure. They're both open to atmospheric pressure, so they cancel out. If we take this level to be the reference level, H2 will be 0 and H1 will be the H. So we'll have a potential energy. What about V1 and V2? V2 is considerably greater than V1 because liquid is constant here. I mean, liquid is static here. Maybe the water level is coming down and it's got a velocity, but the velocity is negligible with respect to V2 because the surface area of here is much greater than the surface area of the jet of water, and therefore the velocity of V1 is negligible with respect to V2. Therefore V1 squared, this term is negligible. At the right hand side we have half of rho v squared, and the rho, if we cancel the rho from two sides, we will get v is equal to radical 2gh. This is the same formula as if we drop something at rest here and it goes in a free fall. It's like a free fall, and we take it at the point 2. So kinematics says v is equal to radical 2gh in the free fall. Okay, now with this velocity, water is leaving this cylindrical container with this horizontal speed, and it has got some time to hit the table here. We want the horizontal distance to be the maximum. Applying the kinematics formula for y direction, in y direction we have this is like a projectile motion, right? Applying the in vertical direction we have delta y is equal to half g t squared, because we have an initial speed in y direction is 0. Therefore, instead of delta y, I put 1 minus h. The traveling time will be calculated here. So the traveling time is 2 times 1 minus h over g. And in x direction, delta x, which is the d, is equal to vt, because it's a uniform motion in x direction. There's no acceleration in x direction. So I replace v with radical 2gh. This is the initial horizontal speed. Of course, the speed remains constant during the flight, and I replace the t with the traveling time. So g cancels out, and I will get 2 out of the radical, h times 1 minus h. So now we want d to be maximum, so d squared, we can think of d squared to be maximum, so h times 1 minus h should be maximum, because h and 1 minus h, their sum is 1, so the product is maximum when they are equal to each other. So we can say h is equal to half meter. When h is equal to half meter, this product is maximum. In other terms, we can, if we want to continue mathematically, we can write d squared is equal to 4 times h minus h squared. And then, for example, if I take the derivative with respect to h, because we want this term to be maximum with respect to h. For example, I take the derivative with respect to h, it will be 4 times 1 minus 2h. And then here we'll find h to be half of meter. Again, the same result. So I use this mathematical trick that when the sum of two terms is constant, their product is maximum when they are equal to each other. So h and 1 minus h, their sum is 1, is constant, so the product is maximum when they are equal to each other. Okay, so we solved it, and I meant to solve it. That's all for now.